Hello. We're doing an extra stream today. I don't usually stream today, but today I am. Looking at this final problem, I was sort of visualizing it, mulling it over. Still haven't massively made any progress, but I'm just going to play around with this for a little bit, see if I can figure anything out about this problem. And then we'll do the next chapter. So probably a reasonably short stream today. But yeah, let's see what we get done. How's my bit rate? Always asking how's my bit rate? It's excellent, obviously. Obviously, it's excellent. Okay, so challenge is, given a sphere S, a great circle of S is the intersection of S with a plane through its center. If a great circle divides S into two parts, a hemisphere is the union of the great circle and one of those parts. So this is crucial because we get the middle. We're allowed the middle. Show that if 5 points are placed arbitrarily on S, then there is a hemisphere that contains 4 of them. So I've got a sphere. I've got a sphere for us to mess around with. And I can add points to it. Sorry the points are a little small, but that's G-plates for you. It's meant for drawing tectonic plates, so it's we're misusing it a little bit. Now, let me get rid of this. There's that blue pointer again. Now, if we want to put like 5 points here, we can sort of see that this is true, right? So I don't think we're as far as proving anything yet, but it would be interesting to try to see if when we get 4, so when we get 3, for example, you might be tempted to think that you can show this just by showing that if you add a 4th point, you will need to put it on the same hemisphere, but this is sort of trivially not true. So if we move obviously over here, then these 4 points are not in the same hemisphere, they are in a different hemisphere. So it's not as simple as that. Now, I guess this, maybe we could do that. In fact, if we just shove a point here, I think if we're very lucky, yeah, we get to have 4 there. But there is a situation in which this is not true if they're like totally opposite. So let's get rid of these and put them at a really obvious totally opposite point. Let's say we've got this, and then we can put 2 others here. Then we could put one, I think, here. And then I think there's no, if I did that exactly right, there's no, yeah, not quite. See, they just won't quite fit into one hemisphere. I mean, it's not very rigorous, but you get the idea, right? So that's one situation where we have 1 on one side and 3 on the other. But then the question is, where do we put our 5th? Is there a way we can put I mean, obviously there's not, but if we really wanted to try to put 5 points on this sphere and not create the situation in which 4 are contained within one hemisphere, we could sort of try. We might think we could put it in the middle, but then obviously we've got this situation, so that won't work. We could put it right over here, and then we've got that situation. We could try to put it on, maybe on the other side. So let's get rid of those and try and bring in our point at the, where'd our point go? I just deleted it. Okay, let's bring it back. We've got 3 there. So let's say we want to put it here. We could try to put it maybe here. And then we got this situation. So that's not going to work. We could try to put it maybe here. No, still we got that situation. We kind of feels like we need to have another point like right on the opposite side. Like right here. Second point there. And I think that's pretty close. But I think, you know, if I had amazing mouse dexterity, which I don't, then I would be able to. So let's look at this. Right, they're all kind of a little bit above. Well, okay, that's not that's not good. Oh yeah, okay. They're all kind of a little bit above this line here. So if we go all the way over here, we said they're also a little bit above this line. So if we're very, very careful, in theory, this hemisphere is the one, right? So in theory, that's the hemisphere. So that's not going to work. Now, let's try and remove one. Let's say if we wanted to put one let's say if we wanted to put one here, we still have the same problem. 4 of them are in this hemisphere. And yeah, what else could we do? So right now they're all in like this hemisphere here, and they're all in this hemisphere here. So if we're thinking about, for example, we're thinking about these. Oh, okay, that's not right. Let me get a nicer color. Think about this. Wow, okay, can't draw a straight line. There we go. It's in like this hemisphere, and it's also in this hemisphere, right? So we've got 2 candidate hemispheres that all 3 of these are in right now. So what can we do? If we wanted to put a firstly, if we put another point here, obviously we've got 4 in the same hemisphere because it's the hemisphere we're looking at. So that's not going to work. So if we really wanted to get a 4th point in a totally different hemisphere, it would have to be on the other side of the circle, or the sphere rather. Let me zoom this out. Oh, that's not good. Well, I guess I've just ruined that. Anyway, it'd have to be in this half for one, and it would have to then be the other side of the sphere, because if we put it in, if we get out, so let's say this is like one hemisphere, right? We've got here, and we need to get it out of that hemisphere. Need to get it out of this one. But we also need to get it out of this one. Like this half we're looking at. Right. Which is kind of promising because that means we've got 4 divisions. We've got, okay, can I draw a sphere? We've got this, and we've got this. Does that divide it into 4? I think it does. Oh, okay. Probably better if I use a different color for this. Okay, that's just totally ruined my spatial perception of what's going on. Okay, so we end up with like this sort of wedge here in this part. This wedge, let's give that a different color. This wedge, that's not the right one, we want to do this. This wedge, and this wedge. Now that's the reason that's good is because the question's sort of telling us something, right? So it's saying like it wants, like the question is leading us via the pigeonhole principle to try to break this sphere down into 4 parts, because anything with 4 parts is going to have anything with 4 parts. Let's say we put these into boxes, right? Let's say we imagine 4 quarters, and we put in 1 point here, 1 point here, 1 point here, 1 point here, and 1 point here. So 5 points. Actually, I'm not even convinced. I felt potentially the problem was leading us to try to split the sphere into 4 parts. Maybe it isn't. Maybe it isn't. Maybe it wants us to. Maybe it wants different parts. Anyway, still seems good. So we need, in order to get. Now we've got these 3 points here. Then in theory we're able to maybe we're able to divide it into 4 chunks. If we want then to put another point on this, then we're going to have to go around the other side, and yeah, because we've sort of put all of these points in like one wedge somehow. 1/4 of the sphere. Maybe that's not always possible. Maybe that's just the fact that we've made it that way. I don't know yet. But another one. But one way we could deal with this situation is is we could go all the way over here, get rid of these, and put a point into this. Whoa, okay. And put a point into this section. So in that way we've put kind of everything in one wedge. Like let's say here. Let's say here. And now we've got something here. Now, let's say there's some way of putting everything into one wedge after 3 points. I don't know if that's true or not yet. But if it was true, and we then have 3 options. We could either put it in this wedge, in which case we've already got 4 in a hemisphere, so we've lost. We could put it in this wedge, same deal. Or we could put it in the opposite wedge, which is what we've done here. Now, hello, Happy Nora. Yes, stream on a Friday is a sad reason. I was supposed to be going out tonight, but I miscalculated the date. And I'm not. So now I have nothing to do. Not that, obviously I have something to do now. But I thought I'd soothe my disappointment by trying to do something much worse, thinking about spheres. How are you doing, Happy Nora? So we got, we could put it in here. Now, that's our only option really at this point. If we were to not do that, if we were to do that, then I suppose we then have three other options. We could put a dot in here, that fails again. We could put it on here, that fails again. We could put another dot in here, which kind of spoils everything. Let's say we do that. Then we've got 2 points in here and 3 points in here. And yeah, then I'm lost again. Then I don't have an answer again. I mean, the real answer, if we look back at the sphere, let's see what the actual answer is. That. Yeah. So what if we like really try and go, yeah, we've still got this one here. Outrageous. Get out of there. We know how to get rid of that one. Oh well, let's just clear it. Okay, so that didn't work. Now, let's say we choose one. Let's say we choose one hemisphere. And by the way, the problem actually involves putting things inside the sphere, I think. But I don't think it matters. I think we can just consider points on the surface. I don't think it matters, but I'm sure it does matter if you want to do this properly. So, all right. So we could think about, let's say, is the problem necessarily 3D, or is it an identical problem on a 2D circles perimeter cut into semicircles, or even a 1D number line cut in half? Good point. I think somebody in the last stream did start by thinking about 2D. So, yeah. Oh, good. That's good. Well, that sounds very nice, Happy Nora. We could indeed put them into. We could indeed do that. We could create two balls, two spheres. All right, let's think about it as 2D then. So in theory, if it's 2D, we just got this right. So I think somebody last stream did have a they. So let's say we got our. It's easier to draw here too. I think it's like 3 and 4 maybe points. Yeah. So yeah, and they're kind of we've got to think about hemispheres as doing like this. So let's say we got this point here. We've got a point here. These are going to be, let's say these are perfectly aligned, so they go in. Ooh, okay. Wish I had lines at this point. Should develop some sort of line drawing system. That would definitely help, huh? Maybe I should draw the lines first. Okay. So let's say, like, yeah, we can put something here. We can put something here. We can put something here. And yeah, is there any hemisphere that we could draw from this point? that would not have two of them in it. So that's from here. Don't think so. Maybe one. But they got to be arbitrary points, right? So here's another attempt. Let's say if we draw them all along this exact center. Now, if we try, like, so we've got 2 points here. Can we add a third in the same, that will always be in the same hemisphere as the first two? So which hemispheres contain these 2 points? We've got this hemisphere going, oh sorry, not hemisphere, semicircle, yeah. We've got this semicircle, and we've got this semicircle going this way. So if we wanted to draw one outside of both, we could draw one here, but then this ends up like on this point. Yeah, I think basically what's most likely is I probably need some geometry for this, right? Probably need at least any facility with geometry. Maybe like above 0 geometry problems done in the last 15 years. That would probably help. That would probably help. I had a feeling also that something about maybe joining these points together like maybe when we have all these points we end up with some sort of division of the circle. Like if we used a triangle for the 2D version, then no matter the triangle we have, I think we can always do like this, right? We can always draw a line through one of the points, dividing the other 2 points, which means there's always going to be a hemisphere with 2 in of the 3. I don't actually remember if it was 2 of the 3. So that's something. Does it apply with, yeah. Can that be applied to the sphere at all? Now, if we have, therefore, let's take 5 points and see what we can actually do with 5 points. Let's imagine we want to draw a square. I did think about drawing a square before. Square being, I guess, 2 triangles. So if we did that, then we could divide this way and this way. This way and this way. No, that wouldn't help. Or maybe we divide this way and this way. If we did that, we would definitely have 3 points on this side. Let's ignore this one. We definitely have 3 points on this side and 3 points on this side. So this divides it into 2 hemispheres. Now we can then either put a point here, in which case we get 4 here, or we can put a point here, we get 4 here. So is that the answer? Let's try some other configurations. So let's look at, I mean, this one's kind of horrible, right? So let's draw lines between all these. Terrible lines, really awful lines. Sorry, my tablet is not treating me well. Yeah, and then we've got this one too. Okay, so this is not a square, but fine. So if we draw, hello, it's Really Ren, how are you doing? So if we then draw these, like this line, for example, let me change my color. So we draw this line between, like covering these 2 points. We extend this line across the sphere. Then we've got 3 points on this side, 3 points on this side, and then we have to then add 2 more points. Which we've got 4 points already, right? So 1, 2, 3. Yeah, we have to add 1 more point. It's got to be on one of these sides. So that adds up to 4. I'm glad you're doing well. Sorry that you've been slumped. I'm all right. I had kind of an interesting day. I taught a bit. Did some teaching today. Teaching is always a bit of a it takes a lot of energy, at least for me. But I enjoyed it. I had some really interesting and engaged learners today. And I also experimented with the new horrifying demon core from Anthropic. It was worse than I expected. By which I mean it was better than I expected. And I was about to go out. I was going to escape from some sort of room. Apparently that's something people do for fun. I don't know why. But then I realized it was the wrong day. So now I'm in here. Now you're trapped in here with me. Yeah, so I'm trying to solve this sphere problem. I think maybe I'm getting somewhere. I was about to touch grass indoors in some sort of room. Horrendous. Yeah, I was kind of sad actually. It's kind of sad. I was looking forward to escaping. But tomorrow I'm going to escape. Going to see my brother. So that will be some good escaping. We won't escape from a room, but we will escape from not seeing each other for 1 or 2 hours, and then we will retreat back into not seeing each other. Anyone got any good weekend plans? It does. The weather indeed does seem to be picking up. It's kind of nice. Yeah. Are you in the UK? Are you not enjoying the weather here, or? Okay. So maybe this is it. Maybe somehow you connect 2 of the points. I mean, can you do this with any 2 points? I actually don't know if you can do it with any 2 points. You can't do it with these points. Or I suppose you could do it with these points. You could do it with these points, but then you win already. You've got 4 on one side already. So it doesn't matter. You could do it with these points and have 4 on one side already. You could do it with these points and have 4 on one side already. Or you could do it with these points, then you need to add 2 more points. The last few days were awful. I guess they were a little bit. Yeah, I guess they were a little, yeah. It has been a little rainy. There was one time where it rained for like 10 minutes and then it was like everything was flooded and I was like, whoa, what is going on? Okay, so maybe there's something there. Now, all of this becomes moot, let's say, when you try and do things horribly. So let's say we add a point here at the very pole, and we add a point here at the very pole. Let's imagine they're exactly positioned. And then we try to add, I mean, let's say they can somehow be in the same hemisphere. And then we, you know, actually I did have a good example of this the other day. By which I mean yesterday. So you have this. And then you have this. This arrangement is kind of awkward. Oh yeah, it's wild. Yeah, the time you can really notice the weather affecting your mood, I think, is like early spring, where you're like, wow, I feel amazing. I'm ready to do anything. And you're like, oh, it's just the sun. the sun has the blue cursor is here, Happy Nora, didn't you notice? I brought it back for you. I went into the code today, I brought it back. Because I knew you'd be difficult about it. There you go. Are you happy now? Are you happy now? Okay. Okay, good. Good. Right, so let's say we have like a situation like this, and we've got, I don't think for this sphere there's any way to get all 4 in the same hemisphere, because if you rotate it this way, you end up losing one. You can capture like both of them here, but you end up losing one of them. So I don't think there's any way you can have these ones in the same hemisphere. So then, can we apply some similar logic? Is there a way we can split this into 2 hemispheres, each of which have 3 points? And indeed there is. We could draw a line. We could draw a line here that connects these 2 points. And then this, no, this would then contain this. We would split these 2 points here. Then we would have 3 points in each hemisphere, at which point the next point will need to be in one of those hemispheres. Happy Nora, you are always happy, aren't you? That is true, actually. That's very true. You're in. But why are you happy? What are you happy about? Wow, my sphere is all off. You don't need to tell me, Happy Nora. If you're happy, that's enough for me. Okay, so kind of, we try to construct. Whoa. Okay. Whoa. We try to we take we try to so we try to construct a triangle. And then we try to take one point and bisect this sphere on it somehow. And then is there any way to not break the rule at this point? We could add one there. We end up with then three points in one, 3 points in here. So we do need more than just one triangle. It's Really Ren asks, for the art of computer programming, you're working your way up to completing. We intend to do all the volumes in the collection. Yes, I am. I am intending to do that. Okay, let's dial this back. So in this situation, we need to construct basically a line between 2 points that splits 2 of the points apart. And we can do this in a number of ways. We can do it this, we can do this, we can do this, we can do this. Hello, Dexter51. How you doing? Now, what is this in a more rigorous sense? Let's say we've got this. Nora is here. Nora's very happy. Hello, Yonder Jazz. How you doing? Maybe it's enough to have a quadrilateral. If you have a quadrilateral like this, you could join together, well, you could take a number of options. You get these 2 crossbars, which allow you to split the circle into hemispheres. Which then means you have 3 on one side and 3 on the other, and the 4th one will add a 4th on one side. Waiting for delivery. Very exciting. Very exciting. What's well, it's probably a bit personal to ask you what the delivery is, but if you feel like sharing, I will I'll be happy to hear. Okay, I think maybe this is it. Okay, let's try this. Let's try this out. Let's say we have 4 points. We've got 4 points on a sphere. If they're inside the sphere, we project them to the edge of the sphere. Doesn't matter whether they're... I don't think it matters if they're in the sphere or not, or on the edge of the sphere. I think we can just treat them on the edge of the sphere. Now, okay, here's a statement. I'm going to state something. Any 4 points on the surface of a sphere, you can connect to form some sort of quadrilateral-like shape. You can also then draw lines between them, between the corners, between the opposite corners. If you do this, you will end up with 3 points on this hemisphere. You'll be dividing it by these crossbar lines into 2 hemispheres. Is that true? Maybe. I don't know enough geometry to say that rigorously, but let's say maybe it is. This divides it into 2 hemispheres. Each hemisphere will have the 2 points that the line is on, which are included, plus 1 extra point. In which case, if you then add 1 more point, it will bring one of the hemispheres to 4 points, and that will mean that it has 4 points, which is the point. That's the point. So there are a number of like steps there, which would be great to have any idea of how to prove those, but I think that is probably beyond me at this point. Now, one of the things I'm worried about is we end up with like points that can't be joined up into squares, into like parallelograms. No, quadrilaterals. Like maybe not. Is there anything we can imagine? This works. Into Jazz. I think it's a bedside table. You recently bought a flat, but you've got until Thursday on your renter, so you're waiting at home to go home. Waiting at home to go home. Huh. Congrats on buying the flat. I don't know if that's as much of an accomplishment where you are as it is in the UK, but well done anyway. Bedside table, yeah. That's the type of thing I never think about. Yeah, Book of Proof, it's kind of cool. It's like Creative Commons, so it's kind of neat. I'm kind of enjoying working through it so far. Bristol, cool. Bristol's a nice city. I was there recently. I went to where is it? Same again. It's a bar. Nice bar. Nice bar. Would recommend if you like cocktails or whiskey. Abinor says, mathematically speaking, the surface is the sphere. The points inside the sphere are not part of the sphere. Wow. It's really weird. Says, I think you would only not be able to form a quadrilateral if all points lie on the same line. Hence, it would form a line. 3 points lie on the same line, then a triangle will be formed. Yeah, that's true. So let's say if we have these points, 1, 2, 3. Now, if we can do that, we have the alternative of just drawing between these 3 points, in which case we get our hemispheres again, and the next 2 points will have to result in either this situation, 4 on this side, or this situation, 4 on this side, or on the same line again, which means either one is fine. Okay, I think I'm moderately satisfied. Yeah, just do add it. If anyone likes cocktails, I can generally recommend a good bar in a number of UK cities. It's kind of a project of mine to go to all of the top 50 in the UK. And so far in Bristol, I went to Filthy 13. Filthy 13's great. Really love that. Really love that place. Same again. Went for the first time recently. Really nice bar. Set up by a few of the people who used to work at Milk Thistle. Milk Thistle was also good. And I haven't been to His Majesty's Secret Service yet, but at some point I will. Left-Handed Giant is a brewery. Cool. Or brew pub, I guess. Brew pub. Oh, yeah, okay. No, it is right next to it. True. Yeah, it does encourage me to touch grass, something that is important for me to do. There's that cursor again. Oh, okay. Okay, I think let me just encode this in some form which is not just like vague intuition. So 1. Whoa. What am I doing? Maybe my teachers are right about me having dyslexia. No, we need 4 points, right? So assign 4 points. If they're on a line, we connect them, and that's like a hemisphere. Let's say you win. Filthy 13's just around the corner. Yeah, Filthy 13 is really, really good. I would recommend, in terms of drinks, they have a great, I should say, I know that I'm not shilling. I guess I am shilling. Basically, any children listening, you shouldn't be here, for 1. 2, don't listen to what I'm about to say. I'm not advertising alcohol, but they do an excellent cocktail called the Scotch and Champagne. It's really lovely. Tastes to me like a good version of what beer. It's like tastes to me like what beer should taste like. I'm not a big beer drinker. I have drunk beer occasionally. Just to me, like Scotch and Champagne is like what beer should taste like in my mind. Like if I had a dream and I drank a beer, the Scotch and Champagne cocktail would be what it would taste like in my mind. Okay, if not, I don't know, draw a quadrilateral. Oh my gosh, it's going. I'm losing it. Quadrilateral. Gosh, that's embarrassing. Okay, draw quadrilateral. Connect the opposite corners. So draw. Basically, we draw. We define the hemisphere. I should probably be noting this down. Yeah, so let's say we've got these. So these are kind of easy because they're all on the same side, right? But let's say they're not. We draw this quadrilateral. We connect 2 of the diagonals. Whoa, okay, come on. Wow, can't draw. We define the hemisphere like this, so it includes 2 of these points and has 1 point on each side. and then we add the 5th point, and then basically it must be in 1. I think. That's my method. I think something like that. We don't get to know the answer because it's an even number question, so we don't get to know Richard's answer, but yeah. Unijazz says, I went to an origami workshop at a cocktail bar called Golden Crane last year. That's cool. That sounds cool. What did you learn to fold? I once went to a cocktail bar in Bristol. It might have been that bar actually. Is it in like a? It's not. Well, the bar I went to, it wasn't underground, but it was kind of like, it was kind of had an underground vibe. It was kind of underground. Like one side had like a kind of road up here, and one side had a road down here. So you were kind of underground, but you were also above ground. Anyway, they made me some sort of old fashioned. It had a full like massive sheet of the black seaweed stuff, nori, just wrapped around it. I ate the whole thing. I think it's supposed to be decoration, but I ate it. Some kind of bird, some kind of boat, a crane, and something else. Sounds like origami. Okay, I'm considering this problem solved. Done. Now, hopefully one day I will come back to it and know more about what I'm talking about. Now, we shouldn't need this anymore. Let's get that to go away. We don't need G plates anymore. Off Park Street near College Green and the crescent-shaped council building, fairly central. Sounds about right. Yeah, nice people there. Yeah, nice people. Okay, so you're here. All approximately 31 of you are here for an important moment, which is this is the first proof chapter proof section that I have read in this book, despite studying it for who knows how long now. Finally, we are about to potentially get to some proving things. And I'm a bit worried that this section is out of sequence and that it's going to expect me to know anything about proving things, which I suppose in theory is going to be introduced in the next section. So I have a hunch that it might be totally undoable by me. But if it is, the chapter after it is called How to Prove Conditional Statements. You can't get more proofy than that. So we'll get to it. Direct proof. Yeah, so I'm pretty sure I'm not going to do this. It's about to get difficult. It's about to get difficult for everybody watching this to see me not not just break like a wave on the beach of this chapter. Okay, let's find out what it's going to say. Combinatorial proof is a method of proof. So just so you know, the book does say the book has a system. Let me show you the system. It's got a system, which is why I'm reading this way. Okay. So this system, sets, logic, counting, and then you can sorry, I'm Just tilting my head. Nobody remark on that. Nobody say head tilt. I've already heard that one. They don't say that anymore, you know. I thought that was quite cute. Okay. 3.5 and 3.6 used in some exercises. Ignore them if chapter 3 is omitted. Oh, okay, there's the... I'm kind of done with the church bells thing. That's better. Right, so it says 1, 2. You can go straight to 4, but you can do 3. There's nothing to say you need anything after chapter 3 to consume chapter 3. However, I have a strong hunch this book is designed to be delivered as a textbook to college courses of some kind. And maybe they're going to play it fast and loose because they're expecting somebody to sort of be hand-holding people through this. Anyway, combinatorial proof is a method of proving two different expressions are equal by showing that they are both answers to the same counting question. Combinatorial, I do this all the time. Combinatorial proof is a method of proving two different expressions are equal by showing that they are both answers to the same counting question. Can you do that? Wow, okay, I guess. Richard Hammock is telling me this. We have already used combinatorial proof without calling it combinatorial proof. Sorry for bashing the microphone. In proving Pascal's formula. Wait, I did that. That's what I did. I did that. Oh, okay. I had some mild assistance, but I kind of did it. Wow, that was tough. That took 2 streams. Not full streams, but it was difficult. Right, so we did this. All right, let's skip the chapter. We did it. Skip it. Then we argued that the left-hand side, is, by definition, the number of k elements subsets of the set such and such and such with such and such. Cardinality of S is equal to n plus 1. There we argued that the left-hand side, this, is by definition the number of k element subsets of this set with the cardinality n plus 1. Okay. I think so. But the right-hand side also gives the number of k element subsets of S, because such a subset can either contain 0 or it does not. We can make any k element subset of S that contains 0 by starting with 0 and selecting k minus 1 other elements from this set in this many ways. We can make any k element subset that does not contain 0 by selecting k elements from such and such, and there are n choose k ways to do this. Thus, n plus 1 choose k, that's the number of k element subsets of this. Well, this is just basically the natural numbers plus 0, including 0. The number of k-element subsets of this is equal to the number of k-element subsets of S with 0 and the number of k-element subsets of S without 0. So this plus 1 is like the 0 in this set, I guess we're saying. Maybe. Both sides count the number of k-element subsets of S, so they are equal. This is combinatorial proof. Okay. we've got an example. Use combinatorial proof to show that n choose k is equal to n choose n minus k. First, by definition, if k is less than 0 or k is greater than n, then both sides are 0 and thus equal. Therefore, for the rest of the proof, we can assume k is between 0 and n, inclusive. The left-hand side, n choose k, is the number of k element subsets of S. K element subsets of S. That's the natural numbers. Up to n. Up to n. Right, up to n. Got it. Every k element subset X, which is a subset of S, pairs with a unique n minus k element subset. Well, I feel like I prefer the notation at this point. The complement of X, which is equal to S minus X, which is a subset of S. Thus, the number of k element subsets of S equals the number of n minus k element subsets of S, which is to say, that equation. We could also derive the same thing by using the formula for n choose k and quickly get this. Okay, so we could use some sort of algebra. But you may feel that the combinatorial proof is slicker because it uses the meanings of the terms. Often it is flat out easier than using formulas, as in the next example. Our next example will prove that k, summing up k through n, n choose k squared is 2n choose n. Really? Okay, you know, that's all right. For any positive integer n, which is to say n choose 0 squared is equal to n choose 1 squared is equal to n choose 2 squared, etc., all the way to n choose n squared, and that's going to equal 2n choose n. For example, if n equals 5, the statement asserts that thing, which is true as both sides equal 2, 5, 2. In general, the statement says that the squares of the entries in the nth row of Pascal's triangle add up to 2n choose n. I feel like I've seen something similar to this in another exercise. Somewhere maybe. Okay, example 3.28. Use a combinatorial proof to show... Well, it's the same thing. All right, so we're going to solve it. First, the right-hand side, 2n choose n, is the number of ways to select n things from a set S that has 2n elements. All right, let me try and actually understand what any of this is about. The right-hand side, 2n choose n, is the number of ways to select n things from a set that has 2n elements. Okay, so let's say if we have, for like n equals 2, we have 4 choose 2, which is 6, which is the number of ways to select n things from a set that has 2n elements. So let's say we've got A, B, C, and D. And we want to select 2 things, in which case we've got A, B, A, C, A, D, B, C, B, D, and then C, D. Yeah, okay, so 6 elements. Okay. Now let's count this in a different way. So what we're trying to say is this is equal to summing... What am I doing here? Summing between n and k starting at 0, n choose k squared. So that's going to be 2 choose 0 plus 2 choose 1 plus 2 choose 2. We know this is going to be 1. This is going to be 1. This will be 2, I guess, because it's like 1, 1, 1. Wait, what is it supposed to be? Just 1? No, it's got to be 2. What is it supposed to be? Oh my gosh. Can't even remember Pascal's triangle now. Yeah, I'm pretty sure that's it. No, I've just made that up. Just made that up, totally. Pascal's triangle is, in fact, not that. It's 1, 1, 1, 1, 2, 1, obviously. Obviously, k. And we've got the 0th row, 1st row, 2nd row. So it will actually be what I thought it was. Made it with 4. But actually these are going to be squared. So we're actually going to end up with 1, 4, 1, which of course will be 6. Okay. Right, now let's count this a different way. Divide S into 2 equal-sized parts. Now S is 2, this is S. Hope you're enjoying the pigeons, everyone. This is S. Now, yeah, divide S into 2 equal-sized parts. S equals A union B, where the cardinality of A is N and the cardinality of B is N. And A intersection B is the empty set. So we're talking about, there are a number of ways to do this, I guess. But we're thinking about, for example, this. Whoa, come on. S2, C and D. 2S. Right. So we're doing that. So we've done that. For any fixed k with where 0 is between 0 and where k is between 0 and n inclusive, we can select n things from S by taking k things from A and n minus things from B for a total of k plus n minus k equals n things. Yeah, okay, so let's say if k was 0, then we would select k things from A and n minus k things from B. And n is 2. So that second term, we're going to select, basically, we're going to select 0 things from A and 2 things from here, so we get CD. Or if we set k to 1, then we'd select one from each, or if we set it to 2, we'd select 2 things from here and 0 things from there. Okay, and we'd end up with n things. By using the multiplication principle, we get n choose k multiplied by n choose n minus k, n elements subsets of S this way. Okay, so let's say if we had 1 for both, we'd then have 2 choose 1 and 2 choose 1, which is going to be 2 by 2, which of course is going to be 4. So I've heard. As k could be any number from 0 to n, the number of ways to select n things from S is thus. Okay, 0 from A, n from B, 1 from A, n minus 1 from B, 2 from A, yeah, okay. But because n choose n minus k and equals n choose k, this expression equals, okay, so it ends up being duplicate. So I guess if we ended up choosing 0 here, let's say if we chose 0 and 2, we'd have 2 choose 0 and 2 choose 2, which would end up being 1 multiplied by 1, which of course is 1 squared. I don't know what that is. Who knows? It's 1. Moment of genius there. Okay, so we end up with that, which is the same thing. In summary, we've counted the ways in which we counted the ways to choose n elements from the set S with 2 methods. One method gives 2n choose n, and the other method gives that other expression, therefore the same. Right, so the structure of this approach is you try to show that there are 2 ways. So you've got your two things that you want to be equal, I guess, and you show that they are both valid ways. They are both equivalent to valid ways of counting the same set. That's what joins them together. And you can invent the set, I guess. But probably the set will be obvious, but you can invent it if you need to. I guess that's the point. Because this is just this isn't anything about sets, really. Like, it sort of is. Like, you can sort of think it's going to be about sets, but there's nothing in the question that forces it to be about sets. Like, I guess you could just solve it algebraically. I guess that's why it talks about that earlier. So yeah, so here we can look at it algebraically, but also we can say we're imagining a set S, and that's where this comes in. And there's like, what I'm noticing is there's lots of like magic in this process where it's like, how are you even coming up with that? But I guess that's it. You just do it. Okay, well, be on the lookout for opportunities to use combinatorial proof and watch for it in your readings outside of this course. Also, try some of the exercises below. Sometimes it takes some creative thinking and false starts before you hit on an idea that works. But once you find it, the solution is usually remarkably simple. Oh, great. Great. Oh, good. That's nice. Nice to know. Remarkably simple. Okay. What do we got here? Use combinatorial proof to solve the following problems. You may assume that any variables m, n, k, and p are non-negative integers. Okay. Show that These are just going to be... I know I'm not going to do any, like all of these. I'll be able to do some, let's hope. I'm hoping for some. Okay, so show that 1 n minus 0, 2 n minus 1, 3 n minus 2, 4 n minus 3, etc. up to n minus 1, 2. What? What? How is that? What is that? What is that? 1 n minus 0, 2 n minus 1, 3 n minus 2, 4 n minus 3, n minus 1, 2, n minus 0, 1. I guess because of the order. Right, okay. So a sequence like this might look like 1 by 5 plus 1, sorry, wrong, 2 by 4 plus 3 by 3 plus 4 by 2 plus 5 by 1 equals, well, n plus 2, choose 3. Right, wow. Yeah, no idea. Sorry. What is going on here? And we're supposed to use the combinatorial proof where we have a set. Well, what's the right-hand side about? N plus 2, choose 3. No, it actually won't be that. It'll be 5. Yeah, sorry, I messed that up. In this case, n is 5. N is 5. So it ends up being 7, choose 3. Three's the term in the middle. It's kind of interesting. Is that the case? No, it's not the case ever because 3 is fixed. But we're choosing 3 from 5 plus 2. The number of ways you can arrange 3 elements from 5 plus, from n plus 2 elements. Now, what would that be about? How many terms are there here? 1, 2, 3, 4, 5. Is there, we could have like maybe one on the front and the back, maybe. I guess this one here is telling us that the set size has got to be 7. So we're thinking about a set of 7 elements. Well, I guess it's going to be like 0 through n. Plus 2. This is gonna, how many does that have? Let's say if n is 1, this will actually have 2 elements. It'll have 0 and 1. So it's actually 1 through n would be 5. So if we had like 0 through n plus 1, so if we could, so we know that this is a way of choosing 3 elements from 7 elements, which I guess is also going to be a way, by the way, of choosing 4 elements from 7 elements, I think. Running out of space. No. Chances of me having made an error here are pretty high anyway. So this would be 7 choose 0, 1, 2, 3, 4. Also noticing, obviously, this tells you what column, what row you're on, right? Probably didn't clock that before. So it's going to be, those will be the same, which is kind of, I don't know. But that's actually a coincidence because 3 is fixed. So, I mean, we will have a comparison, but probably doesn't make much difference. So we've got 1. This would suggest we want to describe it using the addition principle, right? So we've got ways we can choose 3 elements from 7 n plus 2 elements. In this case, 7 elements. So we could pick, let's say if it was A, B, C, D, E, and then F and G also. So we could pick maybe it's about subsets. How many subsets with cardinality 5 of this initial set? Multi-sets, maybe. me keep going along down this line of thought, and then I'll think about multisets. So how many ways are there to choose 5 elements from this? There's, well, also, right, we're talking about this term here. No, we're talking about this term here, which is the sum of these terms, which is the sum of these terms. Which, you know, anyway, so we could choose A, B, C, D, E. We could choose well, there's actually there's 4 ways. There's one way of choosing 5. There's 4 ways of choosing 4. Because you could omit each of these. Etc. No, I got almost nothing. I don't think that's going anywhere. Multisets. What would this be in multisets terms? Permutations, not really. The number of k element multisets that can be made from the elements of an n element set X. Yeah, maybe so. Yeah, maybe. So in that case, we'd be looking at n plus 3 minus 1. Choose 3. And this is, we're talking here about the number of k element multisets that can be made from an n element set X. So we're talking about, let's say if we had a set, let's say if we had our set S. And then we have a multiset which is going to have 3 elements. And so we're then talking about, so we could describe this as, because, you know, just to highlight it, these 2 things are the same thing. Now, if that were true, now what's the question again? What's the question again? So this is like stars and bars type thing. I did think about separators, but I didn't explore it. Yeah, where were we? Yeah, there's no threes on the left hand side. I mean, there are, but they're not special threes. They're like, that's a kind of expansion, I guess. So we want to say that this is also some way of counting a 5-element multiset, of constructing a 3-element multiset from a 5-element set, but it's actually an element set. So it's the number of ways of picking out three elements. Okay, well that's more promising. 3 elements from a n-element multiset. Which would be saying you could what could this mean? What would this mean here? Why would anyone prove anything in this horrible way that requires you to know everything beforehand? Geniuses, maybe. Okay, so yeah, okay, well let's put this in the original terms. Maybe that'll make it clearer. So well, let's say if we have like this situation, and we could have anything. N could be anything. Then we could construct A, or we could construct, for example, A, B, C. We could think about it as maybe we could if we're doing this, then we're picking out like 3 places to put the dividers, the bars. Yeah, I don't think I'm getting anywhere with this. I may give up on this one and try and do some IMO, probably simpler proof exercises. So you just have to sort of guess what any of this means, and I don't think I've got any good guesses. Like, this 1 goes up to n, right? So it refers to the number of elements, which could be 5, could be anything else. So we end up with all 5 elements, which starts to not make sense immediately because we're not choosing 5 elements. So what gives? I guess the other Yeah, well, actually we're choosing 3 dividers, right? So I suppose it doesn't matter how many elements we're choosing. This is just going to be the number of... Maybe this is confusing me more now. It's going to be the number of elements left. So maybe maybe in this case we could say maybe there's one way they could go all at the start. Yeah, no idea. All right. Making no progress on that. Come on, type properly. All right, let's come back to those another day. Those are too tricky for me right now. Okay, let's hopefully get onto some more simplistic material. It's time to prove some theorems. Yeah, I thought it was time a little soon. It's time to prove some theorems. There are various strategies for doing this. We now examine the most straightforward approach, a technique called direct proof. As we begin, it is important to keep in mind the meanings of 3 key terms: theorem, proof, and definition. A theorem is a mathematical statement that is true and can be or has been verified as true. A proof of a theorem is a written verification that shows that the theorem is definitively and unequivocally true. A proof should be understandable and convincing to anyone who has the requisite background and knowledge. This knowledge includes an understanding of the meanings of the mathematical words, phrases, and symbols that occur in the theorem and its proof. It is crucial that both the writer of the proof and the readers of the proof agree on the exact meanings of all the words, for otherwise there is an intolerable level of ambiguity. A definition is an exact, unambiguous explanation of the meaning of a mathematical word or phrase. We will elaborate on the terms theorem and definition in the next 2 sections, and then we will be ready to begin writing proofs. Hi, November Moonrise. What a nice username. Thank you for your kind words. I'm glad that it makes you want to study things more deeply yourself. You definitely should. If you need any encouragement, here it is. Study. The world is full of exciting things to study. They are painful in the same way that lifting weights might be painful, or anything like this is painful, but it is very rewarding activity, and probably will only become more rewarding. Of course, you know this already, but thanks for stopping by. Are you having a good day other than that? Theorems. A theorem is a statement that is true and has been proved to be true. You have encountered many theorems in your mathematical education. Here are some theorems taken from an undergraduate calculus text. Oh, great. They will be familiar to you, though you may not have read all the proofs. Let f be differentiable on an open interval I, and let c be an element of I. If fc is the maximum or minimum value of f on I, then the differential of f for c, I guess, is at c is 0. Okay? If the sum of everything from k to infinity a indexed k converges, then in the limit, I guess, a k is 0. Yeah, unfortunately I don't know any of that. Maybe very vaguely. Suppose f is continuous on the interval a through b, then f is integrable on a through b. Theorem: every absolute Every absolutely convergent series converges. Okay. The problem is that there are so many of them and there's so little time. Ah, true. True. There are so many of them. Somebody said something about this once. Let me see if I can find the quote. Well, the quote is easy to find, but I always find it nice to remember. Again, probably you know this, but I think it's one of the oblique strategies too. I always like to remember that one. Yeah, but there's a lot. There's a lot in the world. Very fortunately, most of what's in the world is totally inexplicable to me, at least. It gives me some sense of where to begin. Okay. Observe that each of these theorems either has the conditional form, if P then Q, or it can be put into that form. The first theorem has an initial sentence, let F be differentiable on an open interval I and let C be a member of I, which sets up some notation, but a conditional statement follows it. The third theorem has form suppose P then Q, but this means the same thing as if P then Q. The last theorem can be re-expressed as if a series is absolutely convergent, then it is convergent. For another example, the equation such and such from example 3.28, page 109, is best phrased as a conditional statement to make clear the assumption that n is an integer. Okay. A theorem of the form if P then Q can be regarded as a device that produces new information from P. Wherever we are dealing with a situation in which P is true, then the theorem guarantees that, in addition, Q is true. Since this kind of expansion of information is useful, theorems of the form if P then Q are very common. But not every theorem is a conditional statement. Some have the form of the biconditional. What's this then? If and only if? I forget exactly how you pronounce it. P-R-R-Q. But as we know, this can be expressed as two conditional statements. Other theorems simply state facts about specific things. For example, here is another theorem from your study of calculus. I love how P mutually implies Q. Aha. Yes. That's good. The harmonic series such and such diverges. I'm really enjoying how it's kind of worrying how much calculus knowledge is implied. In theory, it's in my brain somewhere. I really don't want to review calculus. I really, really don't want to. It would be difficult, or at least awkward, to restate this as a conditional statement. Still, it is true that most theorems are conditional statements. So much of this book will concentrate on that type of theorem. It is important to be aware that there are a number of words that mean essentially the same thing as the word theorem, but are used in slightly different ways. In general, the word theorem is reserved for a statement that is considered important or significant, the Pythagorean theorem, for example. A statement that is true but not as significant is sometimes called a proposition. A lemma is a theorem whose main purpose is to help prove another theorem. A corollary is the result that is an immediate consequence of a theorem or proposition. It is not important that you remember all these words now, for their meanings will become clear with usage. Our main task is to learn how to prove theorems. As the above examples suggest, proving theorems requires a clear understanding of the conditional statement, and that is the main reason we studied it so extensively in Chapter 2. It is also crucial to understand the role of definitions. Okay, definitions. A proof of a theorem should be absolutely convincing. Ambiguity must be avoided. Everyone must agree on the exact meanings of each mathematical term. In chapter 1, we defined the meanings of the sets n, z, r, q, and empty set, which are natural numbers, the integers, the real numbers, the quotient numbers, which I think are also known as the rational numbers, and the empty set, as well as the meanings of the symbols element of and subset of. And we shall make frequent use of these things. Here is another definition we use often. An integer n is even if n equals 2a for some integer a in the integers. Thus, for example, 10 is even because 10 is equal to 2 times 5. Also, according to the definition, 7 is not even because there is no integer a for which 7 is equal to 2a. While there would be nothing wrong in defining an integer to be odd, if it's not even, the following definition is even more concrete. An integer n is odd if n equals 2a plus 1 for some integer a in the integers. Thus 7 is odd because 7 equals 2 multiplied by 3 plus 1. We will use these definitions wherever the concept of even or odd numbers arises. If in a proof a certain number is even, the definition allows us to write it as 2a for an appropriate integer a. If some quantity has form 2b plus 1, where b is an integer, then the definition tells us that the quantity is odd. Definition 4.3. Two integers have the same parity if they are both even or both odd. Otherwise, they have opposite parity. Thus, 5 and minus 17 have the same parity, as do 8 and 0, but 3 and 4 have opposite parity. 2 points about definitions are in order. First, in this book, the word or term being defined appears in boldface type. Second, it is common to express definitions as conditional statements, even though the biconditional would more appropriately convey the meaning. Consider the definition of an even integer. You understand full well that if n is even, then n equals 2a for a in the integers, and if n equals 2a, then n is even. Thus, technically, the definition should read, an integer n is even if and only if n equals 2a for some a in the integers. However, it is an almost universal convention that definitions are phrased in the conditional form, even though they are interpreted as being in the biconditional form. There is really no good reason for this other than economy of words. It is the standard way of writing definitions, and we have to get used to it. Here is another definition we will use often. Definition 4.4. Suppose a and b are integers. We say that a divides b, written a bar b, if b equals ac for some c in the integers. In this case, we also say that a is a divisor of b and that b is a multiple of a. For example, 5 divides 15 because 15 equals 5 by 3. We write this as 5 bar 15. Similarly, 8 bar 32 because 32 equals 8 by 4, and minus 6 bar 6 because 6 equals minus 6 times minus 1. However, 6 does not divide 9 because there is no integer c for which 9 equals 6c. We express this as 6 broken bar, let's say 9 slashed bar, which we read as 6 does not divide 9. Be careful of your interpretation of the symbols. There is a big difference between the expressions a bar b and a divide b. The expression a bar b is a statement, while a divide b is a fraction. For example, a bar 16 is true, and a 8 bar 20 is false. I see. By contrast, 8 over 16 is 0.5 and 8 over 20 is 0.4. These are numbers, not statements. Be careful not to write one when you mean the other. Every integer has a set of integers to divide it. For example, the set of divisors is 6. Of 6 is, for a in the integers, a bar 6, where a bar 6, what do we say? A divides 6 is those numbers. The set of divisors of 5 is those numbers. The set of divisors of 0 is the integers. This brings us to the following definition with which you are already familiar. A number n in the natural numbers is prime if it has exactly two positive divisors, 1 and n. If n has more than two positive divisors, it is called composite. Thus, n is composite if and only if n equals ab for where both a and b are between 1 and n exclusive. For example, 2 is prime, as are 5 and 17. The definition implies that 1 is neither prime nor composite, as it has only one positive divisor, namely 1. Definition 4.6, the greatest common divisor of integers a and b, denoted as GCD a and b, is the largest integer that divides both a and b. The least common multiple of non-zero integers a and b, denoted LCM ab, is the smallest integer in n that is in the natural numbers that is a multiple of both a and b. I do indeed have birdsong on as background music. There are some, at some point there will be some church bells. In approximately 13 minutes, there will be some church bells. So far, happy Nora, indeed. This is seeming annoyingly easy enough for me to be bored. It's still important, but still new information here. Yeah. We got some examples. The expression greatest common divisor of 0 and 0 is problematic. Every integer divides 0, so the only conclusion is that it's infinity. We circumvent this irregularity by simply agreeing to consider GCD a and b where only when a and b are not both 0. Okay. Continuing our examples, we have these other examples. Of course, not all terms can be defined. If every word in a definition were defined, there will be separate definitions for the words that appeared in those definitions, and so on, until the chain of defined terms became circular. Thus, we accept some ideas as being so intuitively clear that they will require no definitions or verifications. For example, we will not find it necessary to define what an integer or a real number is, though we will use these nor will we define addition, multiplication, subtraction, and division, though we will use these operations freely. We accept and use such things as the distributive and commutative properties of addition and multiplication, as well as other standard properties of arithmetic and algebra. As mentioned in section 1.9, we accept as fact the natural ordering of the elements of the natural numbers, the integers, the quotient, the rational numbers, and the real numbers, so that, for example, statements such as 5 is less than 7 and x is less than y implies minus x is greater than minus y do not need to be justified. In addition, we accept the following fact without justification or proof. Fact 4.1. If a and b are integers, then so are their sum, product, and difference. That is, if a and b are in the integers, then a plus b is in the integers, a minus b is in the integers, and a multiplied by b is in the integers. November Moonrise says, I get into trouble with this part of such books because I become bored and start to skim. Then 2 chapters later, I realize I don't really know all the boring parts from chapter 1. Yeah, it's very tempting. It is very tempting to do so. I unfortunately err on the other side and probably waste a bit of time, let's say, going through things that I probably could get away with not going through. It's probably a bit of a teacherly habit. Become too much of a nerd. Yeah. Okay. So we got these. Are we going to get anything interesting soon? No. We're getting nothing interesting for ages. Okay, fine. Okay. I have to keep reading. Oh my gosh. Okay. I'm going to get a drink. I'll be back in approximately 1 minute. Got my dash water. Almost threw it on the floor. Yeah, skipping ahead to the exercises and seeing if you can do them is a good idea. However, I specifically picked this book up because I don't know anything about proofs at all. So this probably is like, you know, eating my vegetables. Lorseya. Dropping the cat drinking. The leafy greens of the mind, true. Need to have more leafy greens. How do we feel about broccoli? Anyone got any strong feelings on broccoli? I've developed an appreciation for it. I never did before. It follows that any combination of integers using the operations plus, minus, and multiply is an integer. Yeah. We also accept as obvious the fact that any integer a can be divided by any positive integer b, resulting in a unique quotient and remainder. This fact, called the division algorithm, was mentioned on page 30. Yes, I remember that. Okay, we're getting some broccoli tips from November Moonrise. Roast it with a bit of oil, sea salt, and paprika. Paprika, as they say here. That does sound good. Having quite a lot of omelettes with paprika at the moment. It's pretty good. Another fact that we will accept without proof, at least for now, is that every natural number greater than 1 has a unique factorization into primes. For example, such and such, yeah. By unique, we mean that any factorization of this into primes will have exactly the same factors. Okay? Thus, for example, there's no, yeah. You may be used to factoring numbers into primes that it seems obvious that there cannot be different prime factorizations of the same number. But in fact, this is still a fundamental result whose proof is not transparent. Nonetheless, we will be content to assume that every natural number greater than 1 has a unique factorization into primes. Great. Good to know. We will introduce other accepted facts as well as definitions as needed. If this guy escalates into category theory, if I even see the word category in this book once, I will have to immediately raid e to the 2 pi I and demand satisfaction. Okay, now we're into direct proof. Okay. This is the whole point, by the way, of the last 2 months. So this better make sense. If this doesn't make any sense, I'm rage quitting. I'm rage quitting everything. If there are any endofunctors anywhere in this book, I'm losing it. You're gonna see, I'm gonna turn into like a rage streamer. Yunjaz says, great with garlic steamed over bouillon as a side to teriyaki glazed tofu. That sounds good. I think I've had something like that. This section explains a simple way to prove theorems or propositions that have the form of conditional statements. The technique is called direct proof. To simplify the discussion, our first examples will involve proving statements that are almost obviously true. Thus, we will call the statements propositions rather than theorems because they're little babies and they don't count. Remember, a proposition is a statement that, although true, is not as significant as a theorem. They're puny. To understand how the technique of direct proof works, suppose we have some proposition of the following form. If P, then Q. This proposition is a conditional statement of form P if and no. P if P then Q. Fine. Our goal is to show that this conditional statement is true. To see how to proceed, wait, we're proving this. Is that right? This is the proposition. To see how to proceed, look at the truth table for P, if P then Q. True, true, yeah. True, false, yeah, fine. It's only false if, yeah, so that's why it's like implies, right? It's only false if P is true and F is false. We're getting a recommendation for Eat Fan from Unijazz. I'll have to check it out. Well, I assume it's a recommendation. Maybe it was terrible, but they still sold the dish. Okay, the table shows that if P is false, yes, this time, yeah. This means that if we are concerned with showing that if P then Q is true, we don't have to worry about the situations in which P is false, as in the last two lines of the table. Sorry, just texting there. Just texting on stream. Outrageous. Still, some people play video games even. Can you imagine? Can you imagine not just studying mathematics for hundreds of hours? Okay, all right, where are we at? If we're concerned with showing P, if P then Q is true, we don't have to worry about the situations in which P is false, as in the last lines of the table, because the statement P, if P then Q will be automatically true in those cases. But we must be very careful about the situations where P is true, as in the first two lines of the table. We must show that the condition of P being true forces Q to be true also. For that means the second line of the table cannot happen. This gives a fundamental outline for proving statements of the form if P then Q. Begin by assuming that P is true. You know, there's a phenomenon in weightlifting where sometimes if you're trying to learn like how to like the correct form for something, you can't have the weight too light. You shouldn't have it too heavy, but if you have the weight too light, it's hard to learn the form because you don't feel what it's actually like to be holding that weight. Here we are again. There we go. That's enough of that. And I feel like this is almost so trivial that I'm losing the point. This gives a fundamental outline for proving statements of the form if P then Q. Begin by assuming that P is true. Right. Okay. We don't need to worry about P being false. Then, and show that this forces Q to be true. So this isn't even a proposition. This is a form of a proposition. Okay, so it's not a proposition. It's like a meta proposition. It's like a form of. It's like a, okay, fine. All right. All right. Fine. I chose to do this. I don't know why I'm complaining. It's got placeholders. It's got placeholders. True. That's a good way to put it. So the setup for direct proof is remarkably simple. The first line of the proof is the sentence suppose P. The last line is the sentence therefore Q. Between the first and the last line we use logic, definitions and standard math facts to transform the statement P into the statement Q. It is common to use the word proof to indicate the beginning of a proof and the symbol It's like a tombstone, right? Tombstone, is that what they call that topographically? To indicate the end. No, so I guess it is a tombstone. It does indicate the end. As our first example, let's prove that if x is odd, then x squared is also odd. So that's our thing. Granted, this is not a terribly impressive result, but we will move on to more significant things in due time. Don't worry. I'm happy with this. November Moonrise. Did it say above that propositions are always true? I don't know. I think it might have done. Where does it define? Where does it define propositions? A statement that is true but not significant is sometimes called a proposition. I guess it has to be proven. A proposition is a statement that, though true, is not as important as a theorem. Yeah. It's saying it's true. I guess we have to prove it's true to make it a proposition, maybe. Okay. The first step, right. We're actually going to get to do something now. The first step in the proof is to fill in the outline for direct proof. For a direct proof. This is a lot like painting a picture where the basic structure is sketched in first. We leave some space between the first and last line of the proof. Uh-oh. The following series of frames indicates the steps you might take to fill in this space with the logical chain of reasoning. November Moonrise is saying the books sit around that, but proof is what takes something from a statement to a proposition. Interesting. Okay. Right. So I'm going to have to learn to write, I feel, to do proving, to prove things. I'm going to have to learn to write. I have to learn to write in an understandable way. See, you see that's a mathematical X. Cool, right? Way cooler than this. That's baby stuff. That's pathetic. If X is odd, then X. Oh no, I almost did it. Then X squared is. Come on, Kay. You've been writing. Also, I mean, it's very fortunate you don't have to be me. Look how I'm gripping this right now. Like, as tight as possible. Like, ridiculous. My handwriting's always been terrible. Goodbye, November Moonrise. Thanks for hanging out. And thank you for the good luck. Okay, proposition. If x is odd, then x squared is odd. And then I guess we write this. So we suppose x is odd, right? So we assume, so we've got like if p then q, and because of the way if then works, we don't care about the situations where p is false. They can be, anything can happen there. Doesn't matter. So we need to. So we start by suppose x is odd. Suppose p is true, and then we need to end with somewhere down here. Something like this. Oh, and then we have this little square. It's the worst. I can't even draw a square. Terrible. It's really Ren. You took a break from the old computer. The maths is mathsing. I attempted to use combinatorial proof and failed. So we're not doing that. We're doing direct proof now. We're beginning to prove things. It's very exciting. I'm creating new knowledge, which other people already know, obviously. Did you touch grass? Everyone's been telling me to do that. Well, no, they haven't. They've been saying, actually, no, I think they have. Failing once is one step closer to success. That's true. Failing twice, 2 steps closer. Okay, now we have written the first and last lines. We need to fill in the space with a chain of reasoning that shows that x being odd forces x squared to be odd. In doing this, it's always advisable to use any definitions that apply. The first line says x is odd, and by definition 4.2 it must be that x equals 2a plus 1 for some a in the integers. So we write this in as our second line. I'm definitely not gonna write all that. Then okay, so then we have then x equals 2a plus 1 for some a in the integers by definition of an odd number. Okay. Right. Now jump down to the last line, which says x squared is odd. Think about what the line immediately above it would have to be in order for us to conclude that x squared is odd. By the definition of an odd number, we would have to have x squared equals 2a plus 1 for some a in the integers. However, the symbol a now appears earlier in the proof in a different context, so we should use a different symbol, say b. Right, so we're alternating between the front and the back, top and the bottom. We're almost there. We can bridge the gap as follows. Thus, x squared equals 2a plus 1 squared equals 4a squared plus 4a plus 1 equals 2a squared plus 2a plus 1. So x squared equals 2b plus 1, where b is the integer, 2a squared plus 2a. Right. So he's sort of putting it in a form. He's putting it in this kind of special. He's putting it in another form. He's putting it in this form so that he can then say this, where b is this. Finally, we may wish to clean up our work and write the proof in paragraph form. Here is our final version. If x is odd, then x squared is odd. Suppose the proof is, suppose x is odd, then x equals 2a plus 1 for some a in the integers, by definition of an odd number. Thus, x squared is equal to, all the way through, equal to 2 multiplied by 2a squared plus 2a plus 1. So, x squared equals 2b plus 1, where b equals, exists, Therefore, x squared is definition by definition of an odd number. So, right. So this definition says if there's an integer solution to this here, then this is odd. So we're sort of, wow, that is really odd. That is really odd. I expected that to be easier. Okay, all right. Well, at least it's gotten a bit difficult. Great. Combinatorial proofs do suck in my experience too, but I imagine I will learn to love them. They're looking better by the second. At least initially, it's a good idea to write the first and last line of your proof first and then fill in the gaps, sometimes by jumping alternately between top and bottom until you meet in the middle, as we did above. This way you are constantly reminded that you are aiming for the statement at the bottom. Sometimes you will leave too much space, sometimes not enough. Sometimes you will get stuck before figuring out what to do. This is normal. Mathematicians do scratch work just as artists do sketches for their paintings. Here's another example. Consider proving the following proposition. Let a, b, and c be integers. If a is divisible by b and b is divisible by c, then a is divisible by c. Let's apply the basic outline for a direct proof. To clarify the procedure, we'll write the proof in stages again. Let a, b, and c be integers. Suppose a is divisible by b and b is divisible by c, so that's the structure of the if-then sort of thing. Our first step is to apply definition 4.4 to the first line. The definition says a is divisible by b means b equals ac for some integer c. But since c already appears in a different context on the first line, we must use a different letter, say d. Similarly, let's use a new letter e in the definition of b is divisible by c. Okay, so by definition 4.4 we know a is divisible by b means, likewise, we've almost bridged the gap. The line immediately above the last line should show that a is divisible by c. According to definition 4.4, this line should say that c equals ax for some integer x. We can get this equation from the lines at the top as follows. Right. Okay. Okay, there are a bunch of them. There's loads of examples. I think I probably just need to do it. Yeah, these will become useful later. In proving a statement is true, we sometimes have to examine multiple cases before showing the statement is true in all possible scenarios. I think I have it the wrong way around. I believe b is divisible by a. A divides b. Okay, I see. Five divides 15. 8 divides 32. Yep, thanks. Thanks for pointing that out. That's true. Thank you, It's Really Ren. Yeah, it is a little counterintuitive. In proving a statement is true, we sometimes have to examine multiple cases before showing the statement is true in all possible scenarios. This section illustrates a few examples. Our examples will concern the expression such as and such. Here is a table showing its value for various integers of n. Okay. Is this always a multiple of 4? We can prove the answer is yes in our next example. Okay. Okay. Okay, then there's loads more. And there's loads more. I'm just going to do one. I'm getting like pretty hungry, so my brain is a little reluctant to do anything, any work. But I'm just going to try and do one. See if I can get anywhere. And I'm going to need to work on this whiteboard so it's a little easier a little faster to write, I think. Okay, so, right, so. The proposition here is this statement, right? If x, oh, I did it wrong, I did the uncool x. If x is, I am indeed writing with an iPad. If x is an even integer, then, oh, to hell with it, x squared is even. Okay. Then we say, what do we say? Proof. It's pretty responsive. It's pretty responsive already. I'm just not very good at writing, basically. Yeah, I don't think I notice any delay now. Okay, proof. So, yeah, what's the structure of that again? Suppose, and then therefore. Yeah, so it's an if-then thing. So we're supposing suppose x is an, probably be faster if I wrote a bit larger. Even integer. Suppose x is an even integer, and then we've got like a therefore. Therefore, x squared is even. Probably wrote it too close, even. Okay, so we have like a definition, right? For this, we've got it's something like x equals 2a. How's this written? Yeah, it's like a then. We've got a then here. Then x equals 2a. I guess we've got a 4. What's the definition again? Yeah. Some integer a, which is an element of the integers. Okay. And then we go at the end too, right? Next we go at the end, thus. Thus. Okay, we're gonna thus. Thus, I guess we do the same thing here. X squared. Hello, Hangyaku. What did you miss? Only my whole life. We're proving things. We're on the road. We're on the road. The whole point, we're getting closer to mathematical induction, which is where the point at which we resume. Yeah, indeed. Okay, thus x squared is also 2, but we have a b here for some integer b. Again in the integers. It's really Ren's dropping some notation. Yeah, I feel like I've seen these somewhere before. So this is implies. We've seen that in the book. Then we've got this for because and this for therefore. Okay, interesting. Oh, I'm so glad, Hanyaku. I'm so glad that I inspired a love of theory of computation. And yeah, thank you for your kind words. I really appreciate it. Okay, now we're supposed to do some work. We're supposed to do something like crazy. We're supposed to transform this into something else. Maybe it's like, let me do this down here. So we could say, we could start off with this, and then we could square both sides. Can we do anything with this? Right, we can do that. And then we've got this, right? Right? Is that right? Is that it? Okay, we have a thus. We're going to have to start writing small again. Really have to... One of the great things about making your own tools is you get the privilege of updating them every time you need to do something new with them. But you also have the privilege of not implementing anything that you don't want. Okay, thus... okay, a little larger than that. X squared equals 2a squared equals, I don't know, 4a squared equals 2 2a squared. So, and then we somehow, yeah, we say, I think this is it. We say so x squared equals 2b where b is the integer 2a squared. All right. Oh yeah, okay, QED. Nailed it. That's how you know it's proven, when you see that. When you see that. X squared equals 2b where b equals 2a squared. Oh yeah. 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 Okay. Cool. So chat, did I prove it? Did I do it? Did I do it? Okay. Did I prove it? Did I prove something today? Has any of this had any meaning? Has any of this been worth anything? I did it. Okay, great. Okay. Who really knows? Yeah. Okay. It was cinema. It was like an extremely actually is cinema. What I'm going to do is I'm going to join up all of the videos, and it's going to become a 50-hour long film, which leading up to this point, and this is the last moment. Nobody do that. YouTube doesn't let you do that. YouTube won't let you upload anything that big, I don't think. Tim Rogers tried it, and he couldn't do it. And I think he's got access to special powers. So, okay, all right, wow, I actually did something. Actually did something for once. She achieved something. Okay, great. Wow. Right. That's my goal accomplished. I'm quitting there today. I got to make some dinner. That's the thing. You always got to eat. That's the thing I mean, people eat on stream. I could never do that. Okay, so everyone, obviously it's Friday evening. Everyone's streaming right now. So in theory, it should be really easy to find somebody to raid. We could even, we raided Stephen Wolfram yesterday. I gotta say, he didn't even shout me out. Stephen Wolfram not shouting me. Doesn't he know who I am? Outrageous. They're raiding that guy again. we raided Stephen Wolfram yesterday. He was pretty cool. He was on a whole thing. He was like locked in. It was like, you know that part of like the Twitch stream where they're playing the video games, they're in like the cinematic section, you can't say anything. That was like everything Stephen Wolfram was doing. He was on some kind of, he could have been proving P equals NP at that point. Like it was wild. It was fun though. I enjoyed raiding him. Very sad not to get the shout out. What I wanted to hear from him was like, oh my god, I just got oh wow, okay, Neo, wow, how was your stream? That's what I wanted from Stephen Wolfram, but he didn't do it. He didn't do it. So, oh my god, making my. I hope this I mean, it's very funny to me anyway. Oh wow, that would be hilarious. One day Donald Knuth's gonna stream. I'm gonna raid him. Okay, is anyone streaming anything? Is anyone streaming anything interesting? Is anyone following? Is anyone I'm following streaming? Oh, well, he's still streaming, obviously. He's still going. He's doing a Q&A, actually. He's doing a Q&A. We could stream. We could raid him again. Okay, anyone got any votes for raiding Stephen Wolfram again? See if we can get the shout out this time. You think we can get the shout out this time from Stephen Wolfram? Get the Wolfram shout out? I think I might just do it. He's doing a Q&A. He's a bit more likely, maybe. He might say something. Okay. Nobody's preventing me. We're gonna do it. We're gonna go check out what Stephen Wolfram's up to. Okay, maybe somebody else. Somebody's got a recommendation. Yeah. The only problem with that person is I can never spell the username. No, we're doing it. We're gonna try one more time. Get the shout out from Stephen Wolfram. We're gonna see. He's doing a Q&A. You could ask Stephen Wolfram any questions you want. What are we doing? I promise I won't do this every time, but we're doing. Oh, hi Atomfire. You're coming in just as we're gonna drop the sick raid on Stephen Wolfram. So obviously be nice. Don't be silly. Don't be silly towards him. He's a lovely, smart person. But we're gonna just the phrase raiding Stephen Wolfram makes me laugh. Okay, we're doing it. Thanks for hanging out. I'm not streaming next Thursday, but I will be streaming next Tuesday. So watch out for that. But I will usually stream Thursday. But I'm away on Thursday. Laters.